Hello, YouTube.
Hello, Mr.
All right, we're going to pretend it's Wednesday,
Oh boy.
and we're going to do this. What are we doing? Find the area bounded by two curves. So you did that for the homework already.
Yeah.
So you did the homework already. I guess you want a homework check-in tomorrow. I could do multiples of 10 or something.
I mean, I have. Yeah.
Multiples of 4, sorry. What? What? I already checked. I asked 10 times. You need to hold it.
I didn't know you could check that.
Yeah, too bad. Okay. All right, now. So what I want to do is I want to talk about how you find the area between two curves, but not using antiderivatives. Now we did this last time. Didn't we use like sigma notation? Yeah. We found we did stuff like this. Didn't we say something like? All right, let's see. What if I gave you this? What does that mean? That doesn't mean anything. Thank you. Wait, hang on. That doesn't mean anything. Ding, ding, ding. What does that mean?
You're adding all integers a to n.
Right. So you plug in 1, you plug in 2, you plug in 3. I'm not doing much. It's just k. It's not like k squared or k plus 2. So you plug in 1, you plug in 2, you plug in 3, you plug in 4, blah, blah, blah. Keep on going until when? N. And we said that adds up to what? We figured that out.
Is that an N?
That's a k, that's a k, that's an n, that's an n.
1 plus n over 2.
Right, the average of the first and the last times how many you got. Right? Didn't we say that?
Yep.
Okay. And that was Gauss's series when he was in kindergarten and all that stuff. Now, I just threw that at you, and I said, well, yeah, because arithmetic sequences, and you know everything about arithmetic sequences because you took precalculus last year in chapter 12. We didn't get to chapter 12 of precalculus last year.
What chapter was that?
Chapter 2, the last chapter in the book, right? No, probably not. Okay, how do you know that this is true? How can you prove that?
Yes.
Oh, yeah.
Oh, let's prove it.
Did we prove it already?
You did? How? How do you prove it?
We did the numbers.
0 to 100.
Prove it for all n.
Yeah.
Any n. Can you prove it for any n?
Yep.
A finite number of n's? A finite arithmetic sequence?
Yes.
Or in this case, a series, we're adding them up?
Of course.
No, yes, maybe? Well, there's Peano's postulates. You know Peano? No? Well, he came up with these things. He says, okay, we can prove by induction. Who knows how to prove by induction? No? Okay. Show that it's true for something. Like, what if I said, what if I just add one term?
1 plus that.
What if I just add one term? I get
1.
1. Is that true that it equals 1 times 1 plus 1? Whoops, I wrote it wrong. I wrote it wrong already? I'm plugging in 1 for n.
I would say that's true.
Is that a true statement? Okay. So show that it's true for 1.
I'm sure it's true for n.
Show that it's true for 2. Any two consecutive integers. Okay. So if I add the first 2, what do I get? 3. Okay, I'm just going to write it this way, but it's 3, right? Okay. And what am I trying to show? That if I plug in 2, I get the same thing, right? If I plug in 2 for n, 2 times 2 plus 1 over 2, do you get 3?
Yeah.
You do, right? All right, so it looks like it's true for those numbers. Is it true for any integer n, I feel like? Well, this is the cascade effect. This is what Peano said. Look, show that it's true for any two integers. If it's true for 2 integers, that's great. Now, let's assume that it works for the next integer, n plus 1, using the fact that it works for some n. If it works for n and n plus 1, and it works for 1 and it works for 2, then it works for 2 and 3, and 3 and 4, and 4 and 5, and 5 forever, right? Okay. So, let's assume that it works for n, and prove that it works for n plus 1. Okay, so show, can't write today. I was at Carnegie Hall at midnight, sorry. Okay, and show that n plus 1 works based on assuming, there's an a in here somewhere, that n works, right? Now remember what it was. N was 1 plus 2 plus 3 plus blah, blah, blah equals n times n plus 1 over 2. All right. Now we're saying 1 plus 2 plus 3 plus blah, blah, blah plus n. Now what?
Plus n plus 1.
Plus 1 more equals what?
N plus 1 times.
Plug in n plus 1 wherever you see n. That's how many, right? So it's n plus 1 for the first n, And what's n plus 1 plus 1?
N plus 2.
N plus 2 over 2. Okay. The average of the first and the last, right? Okay. We're still doing the average of the first and the last. N plus 1 is n plus 2. Average divided by 2, right? Times how many we got? N plus 1 numbers, right?
Yeah.
Okay, now here's the trickery. We're assuming that it works for up to n, because we showed that it works for 1, it works for 2, at least that much, right? Let's call that n as far as it works. And we're going to use that to show that this works. How?
As you know, you can just factor out the part where you had before. It was like
You
n
could
plus 1
okay,
over-
you could replace 1 through n
Yeah.
with this and show that you have an identity. Or there's a lot of ways you could do this. Sometimes you just combine the two equations. You add them, subtract them, multiply them, divide them, something. What if I just subtract the bottom from the top? What happens? The 1s, the 2s, the 3s? Everything cancels on the left-hand side except for what? n plus 1. So you get n plus 1 equals. What do you get on the right side? N plus 1 times n plus 2 over 2. What else? Minus n times n plus 1 over 2. Believe it or not, this is what you had to do if you didn't know that antiderivatives had anything to do with area. Because we didn't use an antiderivative on Monday, did we? Not really. All right, so you just got to show that this is an identity. In other words, like it's a check. Simplify the left side, simplify the right side. Don't cross the equal sign. This is not algebra as far as crossing the equal sign. And show that both sides are identical. They're the same. So is there anything you can simplify on the left-hand side? No. But you can do stuff on the right-hand side, right? All right, so is it true that n plus 1 is equal to this stuff? Well, what are you going to do?
Multiply.
Foil it out, right? N plus 1 times n plus 2. You know how to foil fast?
Yeah.
What is it? N squared plus 3n plus 2. What happens on the right side there? Minus n squared. Minus n squared minus n, because how do you subtract? You add the opposite of everybody. And it's all over a common denominator, isn't it? Over 2? Clean that up. That's really bad. Clean that up a little bit. Okay. All right, so what happens to the n squareds?
Cancel.
What happens to the 3n and the n?
2n.
And you get
Plus 1.
you get stuff. N plus 1 equals 2n plus 2 over 2. But what did you say about that? The 2's go into both, the denominator goes into both, the monomial goes into both terms of the binomial, and you get n plus 1 equals n plus 1, which is true for all n. Check. That's an inductive proof. Okay, so if it's true for any two consecutive integers, 1 and 2, then you can assume, if you assume that it's good for n and show that it's n plus 1 is good too, it's good for 2 and 3, 3 and 4, for whatever the heck you want. All right, so I will say that this is true. We just proved this, right? Similarly, you can prove this. Let's see, what do I need? This takes a lot longer to prove, so I'm not gonna. But this. What am I doing? Adding up the first n perfect squares, right? So 1 plus 4 plus 9 plus ... n squared is, believe it or not, oh God, n times n plus 1 times 2n plus 1 all over 6. Oy. Which you can also prove inductively, but we will not right now. Tune into pre-calculus screencasts. And how about this one? 1 plus 8 plus 27 plus all the way up to wherever you want to stop. Believe it or not, is this weird? Are you ready? As it turns out, that's true. Okay? It's a square of the first sum. All right, so we're going to use that. Here we go.
What about k to the 4th?
Well, let's not go there right now. Yeah. Okay, so this is what I want to do. Don't change. I want to find the area bounded by the curve y equals x squared from 0 to 5. Now, last time we did y equals x. It was just a line, and you didn't have to do antiderivatives. You didn't have to do this. It was just a triangle. Silly example. Now it's a curve. Y equals x squared is a parabola, right? Okay, so how do you do this? Now, that's modern notation, because we know what we're really doing is we're adding up infinitely many Riemann rectangles that are infinitesimally thin, right? And that's what that weird symbol there that is an S, a sum, right? Let's say we don't know that yet. I want the limit, as n goes to infinity, of all the right Riemann sum rectangles for x squared from 0 to 5 with n rectangles. All right, that's old notation. Because they didn't know anything about what's the antiderivative of x squared. Shh, don't tell anybody. What's the antiderivative of x squared? Don't tell anybody. Just me. X squared over 3, right? They didn't know about this stuff. Okay.
Is that a subscript n?
That's subscript n. We're talking about n rectangles. Okay? But n is going to infinity. Okay. So, remember how this works? It's a limit as n goes to infinity. All right, so each rectangle has a base and a height, right?
Yep.
So each base is what? They're all the same.
Yep.
We factored that out? Okay, so we called that what? Do you remember? Delta x, okay. Times the height of each rectangle. Okay, if we're starting at 0, A is 0, B is 5. And, okay. Where's the first height? You have a rectangle, right? Here's the first rectangle. Here's 0. Here's the first width. Where are you taking the height if it's a right rectangle?
0 plus the width.
On the right side, right? So what's the height?
Squared.
It's this function value at x. What's the x there? It's only one width. What's the x value here?
Delta
Delta
x.
x. So it's delta x squared. Okay, plus. Now what? Well, let's see. That's the first rectangle. Now we're going to move over to the next rectangle. The width is still delta x, but where's the end point? 2 delta x's. And you're going to take the function value there to get the height. Okay. Plus, by the way, let's be consistent in the notation here. The x coordinate of the right side of the first rectangle squared, because we're plugging that into the function x squared to get the height.
Why don't we just factor that
Plus the next height squared. Plus, what's the next height? 3. Okay.
Why don't we just factor that?
You want to factor out stuff, right? Okay. All right. Plus, when do you stop? What's the last rectangle?
N delta x.
N delta x's, right. Okay. Now remember, what is n times delta x? What was delta x again? Delta x equals b minus a over n. If you multiply that by n, you get b minus a,
Which is 5.
which is 5 because a is 0.
Yep.
Right? Okay. All right, so... Alrighty. So let's simplify stuff. Every term has a delta x squared in it, right? And we have a delta x here, right? Can we factor all that out? But what's left then? If you take out delta x squared here, and delta x squared here, and delta x squared, what's left? 1 squared, 2 squared, 3 squared. Does that sound familiar? All right, so I have a delta x cubed, right? I took out delta x squared? Okay. I'm going to write this. Times 1 squared plus 2 squared plus 3 squared plus... Okay. So what are you going to do with that? Right? Really?
Substitute in the
Right, isn't that what we just said?
Yep.
It's delta x cubed times sigma as k goes from 1 to n of k squared. Right?
Yep.
Okay. So let's simplify stuff. Delta x is really what? Well, you just said b minus a is what here? We want the integral from 0 to 5. 0 for a, 5 for b. So b minus a is what?
5 over n.
So that's 5 over n. So I want the limit as n goes to infinity of 5 over n all cubed times that thing that we said. N times n plus 1 times 2n plus 1 over 6. All right, so let's write that. N times n plus 1 times 2n plus 1. Go away. Stop it.
Just keep writing.
Okay, so n, give me a pen. Why is my pen gone? Times n plus 1 times 2n plus 1 over 6. Okay. So how do you take that limit? Well, 5 cubed is
125.
125. How about if I do this?
5 over 6.
Can I take out the constant multiplier? Okay. And so what do we got? We got, well, how about we distribute this first n? What do you got? N squared plus n times 2n plus 1. Why is this not lining up right today? Or any day for that matter. All over what? N cubed. All right, so does this limit exist? Is this top heavy, bottom heavy, or equal degree? Equal degree. And what's the leading coefficient? Because equal degree, all you have to do is divide the leading coefficients. On the bottom, I got a 1. On the top, if you FOIL this out, what's the first coefficient going to be? 2. And what about that limit is then 2. What about the 6? Did you expect that result? Why did you?
Because you know antiderivatives.
If you think antiderivatives, right? Okay, if you FOIL, I don't feel like FOIling this out. If you FOIL this out, first times first is going to be 2n cubed, right? So the leading coefficient here, the leading term is going to be 2n cubed. The leading term here is just n cubed. There's only, right? And remember, we figured out these kinds of problems if you do L'Hopital. We'll get to L'Hopital again. All you end up with is the limit is the first coefficient on top divided by the first coefficient on the bottom. 2 over 1 is 2. That's the limit. So you got 2 over 6 is really, this is 2. This whole thing is just 2. Over 6 is 1 over 3. Just reduce. Just reduce in practice.
Why did you keep the top the same?
Huh?
I have no idea.
Okay, this is what I'm saying. You ready?
Don't you multiply the 2 by the 125?
Yeah, I'm saying, but this is what I'm saying.
You get 25 over 3.
How do you multiply fractions? 2 over 1, multiply numerator times numerator and denominator times denominator, or reduce if you can. And 2 into 6 goes 3. You can multiply first if you want and get what? 250, 6, and then reduce, whatever. And is that expected? Well, remember what the question was. Now let's pretend we're in the 21st century. Nobody does it like that anymore. Well, we did. So I'll go back 1 sec. How do you do this nowadays? The antiderivative is what? X cubed over 3, evaluated from 0 to 5. So you plug in first, the order matters? 5. Then plug in 0 and subtract. And don't you get what we said? Amazing. All right, who missed the last part of that?
Wait, is 5a or is 0a?
And when you go the integral from 0 to 5, a is the bottom. A is 0, b is 5, and n is how many rectangles you want. So now we're running a little short on time, but you could do this for.
Anything.
You got it? You got it? Okay. You could do this for x cubed too, the same way, using this result. And n to the 4th and n to the 5th. There's results for that. Okay. So now, all right, let's be more modern. So, riddle me this. Do it the modern way. Antiderivative, x squared over 2 evaluated from 0 to 1 is going to be 1/2. Okay. The area from 0 to 1 bounded by y equals x squared and the x-axis would be what antiderivative? X cubed over 3 evaluated from 0 to 1 is going to be 1/3. Okay. And just for fun, okay. Now this was the question. What's the area bounded between two curves? There's y equals x. There's y equals x squared. There's y equals x cubed. What if I want the area between x squared and x cubed? Subtract the area bounded by x squared and the x-axis, which we had was, you forgot? 1/3. Minus the area bounded by x cubed in the x-axis, which was, so I'm going to say the area bounded between x squared and x cubed is the higher minus the lower. And that's going to be 1/3 minus 1/4. And, okay, do you know how to subtract fractions? We just added fractions before. We multiply fractions. Okay, common denominator is 12. Multiply top and bottom by what on the first one? 4. So I got 4/12 minus 3/12 is 1/12. Amazing. That's how you get the area between two curves. Isn't it amazing? Now, what if we did this the newfangled way? What's the antiderivative of x squared? X cubed over 3 minus then x to the 4th over 4 evaluated from 0 to 1 is clearly 1/3 minus 1/4 is 1/12. Okay. What if I want the area between x and x squared? Why am I subtracting x squared from x? I thought I was supposed to subtract the higher minus the lower. Well, the higher function is x for values less than 1. When you square a number less than 1, what happens to it? Let's say 1/2. Square it. Well, it gets smaller, right? Okay, so this is really smaller when you square it, right? The x squared is smaller than the x when you square it because you're in the domain from 0 to 1. All right, so what do you get for the first antiderivative? X squared over 2 minus then x cubed over 3, and we already figured out each one of these was 1/2 minus 1/3. Okay, common denominator now is 6. Multiply top bottom by, so you get 3/6 minus 2/6 is 1/6. Okay. All right, so what are we doing tomorrow? We're going to program this beast and do lots and lots of ends, rectangles. Yeah.
We had to do the whole way, like when you touch it, give us.
Do you have to do it the other way? No. I would give it all that. I don't know.
Yeah.
Well, I will see.
One bonus, and it has to be that.
All right, see you, YouTube. Have a nice